A very good evening to everyone. We, the team of Petroleum Engineers Association, is delighted to organize this webinar session on the theme Challenges in Petrophysical Characterization of Organic Rich Cells and Tight Gas Sands. We are very pleased to introduce Dr. Bhaskar Sharma, sir, who will be our speaker for today's session. Dr. Bhaskar Sharma is an engineer consultant Texas, endowed with 23 years of experience. Dr. Sharma's formation evolution experience ranges from the darkest carbonate of Gawar Basin in Saudi Arabia to the nano dark sand and carbonate of North America. His Halliburton over the last 13 years stabilized him as a petrophysicist, both in the field of unconventional and conventional reservoir. His role as a senior advisor in petrophysics presented him with the opportunity to collaborate with knowledgeable operators in the North America land basin in evaluating and developing their assets. Dr. Sharma did his master's in applied geology from University of Roorkee, India, and completed his PhD research in geology from Guwahati University, India. As an avid researcher in the field of geology and petrophysics, Dr. Sharma has several papers in SPE, SPWALA, and AAPG to his credit. Now we will also post in the video on our YouTube channel so that you can access anytime. Now I would like Dr. Bhaskar Sharma sir to start the session by sharing their knowledge on the challenges in petrophysical characterization of organic rich cells and tight gas sand. Thank you.
Thank you for the introduction, Nikhil. Hello, everyone. Welcome to this presentation. I think most of the people are joining from India, and there are quite a significant people are joining from other countries as well. I welcome you all and really appreciate you joining this presentation on a late Friday afternoon. Thank you for that. And I hope you all are doing all right and staying safe. So going into this presentation, we're going to talk mostly on the petrophysical characterization of organic rich shales and tight gas sand. This is a topic that I've been involved for almost nearly last 10 years in North America land. And it has its own challenges. And people may say that there are challenges in organic reservoirs as well. That is true. We have challenges in carbonates, we have challenges in plastic rocks, or we have challenges in turbidite sands. But this challenge, the presence of particularly organic rich shales, which has the presence of organics, it alters all conventional logging responses. So how to unmask the real characterization out of that, that is one of the most challenging factor. So that's why it's I really like doing this because of the fact that it is very challenging, right? And as well, also I've been involved in this for the last nearly 10 years. So if we look at the, let me see my screen, okay. The growth or the development of the unconventionals in North America land, I'm showing this map here of the lower 48 states of North America. You can see that it's been scattered or it's been spread well over entire North America. And last 10 to 15 years, actually it has contributed quite significantly, and it has put significantly to the production of the hydrocarbon in North America. And it has put North America into the first or the top 3 global producers, along with Saudi Arabia and Russia, right? So it's a long learning curve, lot of trial and error, lot of experience been gathered, and that experience with that, that experience, we can employ that now in elsewhere in the rest of the world. But keep one thing in your mind, that all these unconventionals, mostly the organic rich shales, even though they are being called the organic rich shales, they are quite different lithologically, whether in terms of clay content, whether in terms of carbonates or presence of, the sand volume, organics, organic maturity, production pattern, gas window, oil window, all of them are quite significant. There are a lot of variations within that terminology. It's not showing it as a one it's not a one thing that, you know, you have one particular set of solutions that will be applied for everyone. So I think I can stop my video. It will be distracting otherwise. Okay, so the next slide I'm showing here is the spread of these unconventionals all around the world. And you know, it has not been so active as you can see in North America, of course. Sparing a few like the Vaca Muerta in Argentina, where it has started developing the unconventionals there quite significantly. And there are some in Eastern Europe, and there's some development in China as well. But when we look at, look at the development in the North America, and if we employ that experience here, I think we can definitely shorten that learning curve and make it more economically viable and you know, and cost effective in going forward. But as you can see, it's well spread all around, and it has you know, all the continents, and it is present. So there's significant opportunity out there. Just a matter of getting it, you know, cost effective, or optimizing the whole operations. So now, just before going into more detail into the you know, the unconventionals, let's first understand what is these unconventionals are. I'm well, as I put the title of this presentation, I will confine myself only to the organic rich shales and the tight gas sand. I'm not going to talk about the coal bed methane or the tar sand, etc. Because for the last 10, 15 years, as I say, when we're talking about unconventionals in the North America, it was mostly referring to the tight gas sand and the organic rich shales. So this is a little busy slide, but if you look at it, let me put the laser pointer. Okay, so I believe you can see my laser pointer now. So in the top here, this scale is showing the permeability range. Okay, it is on the left hand side, it's a sub-nano Darcy permeability. So that means it's extremely tight, very low deliverability, or you know, of the reservoir. The reservoir, those are within this area, and then it's increasing gradually towards Darcy or thousands of Darcy rocks, going towards the left side of the stream. So here you can think of the reservoirs like the Saudi, you know, the Arab D formation, maybe in the Ghawar basin, that are Darcy rocks, or it's a very high permeability. And then as you move towards right, you can think of the extreme is the source rock reservoirs particularly the gas source rock reservoirs in the North America, maybe the Marcellus or the Haynesville. Those are extremely low permeability rocks. Those are nanodarcy rocks. So one thing is here that, you know, these rocks, if you have enough reservoir pressure, you can produce by themselves. You do not have to do any reservoir stimulation in them. But on the other hand, these rocks here, the organic source rocks, or whether it's in the tight gas sand, I can give you an example of, say, the Cotton Valley tight sand that is in the North America, in North Louisiana or East Texas. And those are significantly tight. They are in the range of lower microdarcy to microdarcy range. And some of them are actually falling into even upper nanodarcy occasionally. But so you can see, like, you know, all these tight gas or the source rock reservoirs, without a reservoir stimulation, you cannot produce. You have to create a conductive path when putting the proppants there and let the reservoir flow. Otherwise, it cannot flow. You have to create a good, big enough surface area to drain this hydrocarbon going into the wellbore in order to be produced. So that's the most, I mean, broadly differentiator there with the conventionals, right? And the lower scale here is showing you the radius of the pore size. So here it's in the millimeter, or, you know, micrometer, nanometer diameter. So for your reference, you can see the dry gas or the methane molecule size, which falls here. And as you move towards left, like the scale above, it's increasing in the pore size. One thing you have to keep it in mind that the pore size, as the pore size increases, the reservoir deliverability and capacity increases as well. Of course, there's few other factors as well, connectivity and all, but in general, that is the trend. Um, those of you who are doing the sorting, grain size sorting analysis and all, you are familiar with this kind of mesh size. So you can see in comparison to the scale, the 400 mesh size, which is extremely fine, is actually here. And we are talking about a reservoir in this range, which is way more finer or smaller grains, or smaller pore size than that. Just to give you an idea what we are dealing with. So that's how, this is the very extremely small pores, very low deliverability, extremely low permeability are what we are going to talk about today. So as you see, they are both quite different as well. I mean, when I'm talking about the tight gas sand and the source rock reservoir, the major difference is that the source rock, when I'm saying source rock, those are the organic source, and the organic rich rocks. And the other one, the tight gas sand, generally the one that we're talking about is not having organics in them. So both of them have their own characteristics and they are different as well, at least in our approach of how we can characterize. So we're going to treat them both separately. Okay. So I'm going to first talk about the challenges that we see or come across in the organic rich shales. So as a petrophysicist or a formation evaluationist, our primary duty is to quantify the reservoir storage capacity and how much of those stores are filled with hydrocarbon, and whether that hydrocarbon is movable or not, and how much we can produce, and whether the reservoir has the reservoir deliverable capacity. So these are the three or four basic components of our as a petrophysicist that we have to deliver, right? That's based on which you take the company that you work for takes, or the project you're working for will take most of the economic decisions on. So you need to quantify those things. But those are the things, or those are the parameters that are the most challenging to determine in the unconventionals, particularly in the organic rich shales. So here you can see my first parameter that I am showing here, and that is the porosity determination. That's a very basic thing that we need to know how much of a storage we have in these reservoir rocks, right? A conventional wireline tool, when you think about it, particularly for determination of porosity, it is either the density tool or the neutron tool or a sonic tool. And all these tools, the response in presence of organics are getting significantly altered. So it doesn't give you a true porosity. So even if you combine to come up with a cross-plot porosity, your metrics will be not right, or we'll look into a little bit more detail. So we need some tool that is not dependent on lithology. For example, like a density tool is a lithology dependent tool, right? Because you measure the density, and then when you convert it to porosity, you have to assume a certain matrix, whether it's limestone, sandstone, dolomite, you have to come up with a certain density number, and then you convert that to porosity. Same thing goes for neutron as well. Neutron, when you're logging neutron, you have to assume a matrix that is either sandstone, limestone, or dolomite. And then that is the reason, actually, one of the reasons where even in the conventional porosity determinations, we do not go with only one particular porosity tool, but we have different porosity tools, and then we combine them to come up with a true porosity. Here, the big problem is that, this density and the neutron are heavily altered because of the presence of the organics in these rocks, and it's created a huge problem in determination of the true porosity. So you guys have probably heard about NMR and the nuclear magnetic resonance. Nuclear magnetic resonance is quite unique in this sense that it doesn't depend on lithology. So it's a lithology independent tool. So whatever porosity we get from them is actually quite very close to the real actual porosity. So we'll get into that a little bit. We'll look into a little bit in more detail. We are talking about the organics. So quantification of the organics is the next step. That's very critical for us to know in these rocks, because these you can think of it as a source, it's a source rock, right? So here, the whatever the hydrocarbon been generated, it has not migrated away from the source. It is staying within the source. Most of the time, it is within the organics. Organics, when it transforms to kerosene, it has porosities in that within that as well. And so quantifying the organic is very critical for us to understand and to know. So that's why, that is the second step that we need to understand, and also the maturity and all this. But that's by itself quite a science in characterizing the reservoir. The next point is the mineral volumes. So in conventional wireline logging, when we talk about the triple combo or a quad combo, triple combo, this terminology used for when you run with a density neutron, resistivity, gamma ray, and that is considered as the basic triple combo. And quad combo is then when you add the sonic log to that, and that's generally the conventional terminology for quad. And generally, those are whether you use a deterministic approach or a probabilistic approach, you have limited number of uh, input equations, so your outputs are limited as well. And in organic rich rocks, we know that this is not a clean reservoir. We have quite a significant amount of clay or the shale there. So understanding the clay, what kind of clay, or quantifying the clay volume or the shale volume is very critical. And this is both for production as well as for the stimulation engineers as well, because they need to understand the clay volume, because they have to design their reactiveness of the clay with the fluid, fracture fluid or drilling fluid, and also to understand how ductile they are, to have an estimate for their fracture, height growth, etc. As well as when you're talking about placing propant or creating a fracture, what kind of embedment they might be looking at. So those kind of things, quantification of the mineral volumes, or particularly the clay, is very critical. Also, you will notice that you will notice in a few later slides that a good estimate of the different mineral volumes can help us actually in some other aspects as well. A true determination of grain density also is pretty important for us. I mean, that gives us a porosity measurement, right? So quantifying each of these mineral components in the rocks and come up with a good grain density is of utmost importance as well. Presence of organics alters the resistivity response to the rocks as well. In a conventional reservoir, our saturation models are mostly based on resistivity measurement, right? So once you determine your porosity, then your resistivity is a good indicator for presence of hydrocarbon and water. And we take advantage of that, and then we quantify the water saturations and the resistivity from the resistivity. But here, because of the presence of organics, when you think about it, the organics are transformed into kerosene, and then with maturity, it has started producing hydrocarbon, and so there is no water coming into the system. It's all mostly hydrocarbon wet. There are a few papers recently which are showing about having water in the probable water in the kerosene also. Well, we're not going into that debate now, but staying with this presentation, in general, you can consider that as a hydrocarbon wet system. So just imagine a rock with hydrocarbon and entirely hydrocarbon wet without water, at least the kerosene portion of it, the resistivity will shoot up quite considerably. So your resistivity become very high. So when you derive your saturations based on those resistivity, it gives you some erroneous water saturations or hydrocarbon saturations. So you have to find a way or some different tools that can be helpful in determining the water saturations. And then comes the rock mechanical properties, because as I mentioned, these rocks need to be reservoir stimulated. So this is in the unconventionals, a petrophysicist or a formation evaluation person always works very closely with the reservoir stimulation group. So that is, in a conventional, probably it's not needed, but here you collaborate with your the frac team or the reservoir stimulation team to optimize the whole well treatment and production for the production of a particular well. So you work not only, you just don't look at only your petrophysical properties, but you have to be engaged into doing rock mechanical properties and have an understanding on the fracture height growth, or which are the different kind of rocks that you are being able to frac easily, and tie them back to your estimated rock mechanical properties. So that's how it's all integrated solution that you have to consider. So that's why it's very challenging. So now let's go and look into it a little bit into more detail, each one of them. So the first thing I'm going to talk about is the porosity determination. So density, as I mentioned, is density and neutron both are metrics based, right? So you need to know the matrix density or what metrics you are using to log for the neutron porosity. So density measurement tool, it measures the density, and then we convert that to porosity. So if you look at all the most of the rock forming minerals, they are either silicate or aluminosilicate or phosphates. Maybe some of them are the carbonates or the sulfides, right? So these are all a density higher than 2.5 or 2.6 gram per cc. I'm just giving a lower number. But the density of kerosene is extremely low. Its density of kerosene can range from about 0.9 gram per cc to about 1.2, 1.3, and some cases very high matured kerosene can go even higher. But in an average, we can think of it as a number about 1.1 to 1.2 gram per cc. So just imagine now what will be the density response to that. So if you have, say, 15 to 20% of organics present in these rocks, so 15 or 20% of the volume where the density measurement is coming from is from the organics, which is fairly low, about 1.1 or 1.2 gram per cc, as compared to rest of the minerals, maybe 2.6, 2.7 gram per cc. So your density would read low, and when you convert that to porosity, it will give you a very high porosity. But this is not real, right? Because kerosene has porosities within it, but it has a dry matrix also. So all that of kerosene is not porosity. So it's giving you a false impression that you have a large reserve of storage because of the presence of the organics. So that's why you have to somehow account for that, but you cannot account for it at the very beginning because you don't know how much kerosene volume is down there. So you need to quantify that. So that is the reason why density measurement, when converting to porosity in organic rich rocks, fall apart, and you cannot convert it directly. Same thing goes for neutron. Neutron response in the organics is fairly high. If you consider a rock entirely of kerosene volume, that will probably show a porosity in the range of 63 to 64%. That's fairly high, right? So when you have kerosene presence, say 15, 20%, that will also increase your neutron response. So as a result, now you can see that both density and neutron are giving you erroneous porosity response because of the presence of the organics. And as we said earlier, the NMR, on the other hand, is giving you a good porosity irrespective of lithology. It's a lithology independent tool. Remember that, because that's very critical. But only problem with NMR is that it is dependent on the hydrogen index. So if you have lighter hydrocarbons or gas, and that's where because it looks at the hydrogen protons, right? So if you are gas as compared to oil, you are looking at lesser number of hydrogen protons, so it gives you a lower porosity number. But in these rocks, if you remember my first, the third slide where we are showing the pore size are so extremely small that it really doesn't matter whether you have gas or lighter hydrocarbon, because NMR, as you know, it is composed of its response comes from bulk response comes from bulk relaxivity or surface relaxivity or diffusion. Here, since we do not have the bulk, because it's the small pore size are so small, the surface relaxivity is the most dominant one. So in such situations, that hydrogen index effect doesn't happen. So that's why we get a very good porosity out of the NMR. Just continuing with that, Sorry. So here in this slide, on the right-hand side figure, I'm showing three wells from the Eagle Ford. This is taken from a paper that was presented in SPE. And here in the first track, where my cursor is the mineral volumes, and then the green indicating clay, the yellow indicating sand, and this the magenta color showing the kerogen volume, and then porosity here as well. And in the second track, I'm showing this is the NMR porosity on this black curve here. And all these red dots are coming from uh, the core analysis. Core for unconventionals, the conventional approach of core analysis also doesn't work. You have to find a different way. Well, generally, a common way that has been pretty useful was the GRI, the crust rock GRI method to determination of porosity. And you can see like this well has a fairly good correlation with varying a few points. I mean, most of them are fairly good correlation with the NMR porosity directly, right? Without any corrections or anything. And the same thing goes for the second well and the third well as well. And this is all Eagle Ford, but I have seen a similar response in whether in the Marcellus, which is significantly different in lithology, or the Haynesville or the Woodford, you name it, and all of these organic rich rocks actually have a very, the NMR response seems to work perfectly well, and it matches with the GRI kind of porosity fairly well. So um, so at least one part of the puzzle is solved here. So if we use the NMR, then we get a good porosity irrespective of lithology, right? So we got the reservoir storage understanding from this. The second point here is the quantification of the organics. So quantification of organics, when you're using log interpretation, we have multiple different ways we can employ. But just remember, these are all indirect methods, okay? One of the very common or very um, earlier method was the delta log R by Quantification. And that method uses density, neutron, sonic curves along with resistivity. Then basically it overlay the curves in a non-organic rocks, and then the separation in the organic rich rocks you can quantify to come up with the volume of organics in the rocks. So that's one method, but that one method doesn't work everywhere. As I said, all the organic rich rocks are varying in composition quite significantly, so it doesn't work everywhere. Then the other equation works is called the smoker equation. The smoker equation is also dependent on the resistivity, the density, and also it takes into account the density of the kerogen or density of the matrix as well. And that seems to work quite well in some of them. For example, like in the Utica Point Pleasant, that's another organic rich shale just below the Marcellus. It works fairly well there, and also in the Eagle Ford, it seems to work perfectly as well. And then, as you know, when you have a significant amount of kerogen present, it lowers the density measurement, right? So you can derive some equations or some regressions from using different density relations with them and come up with a organic volume. So that's why you have all these different density regression equations. And then I have some slides, we're going to discuss those. There is this, in some areas, particularly in the Marcellus or in the Woodford, there is a strong correlation with presence of uranium. Uranium makes the gamma ray hot. I mean, generally gamma ray, when we plot it in the scale of 0 to 150, in these scenarios, the gamma ray can be reading very high, going to some 700 to 800 API in the Marcellus. And but it's because of the presence of very high uranium, and somehow that uranium seems to correlate fairly well with the presence of the organics in that. So you can use that PAM uranium as an indicator of kerogen, and you can quantify that. And then also there are some relationship with pyrite. But one very common and the most useful method that I rely quite heavily on is a cross plot versus the NMR porosity. As you know, the cross plot is a density. You get a cross plot from a density and neutron using a density neutron cross plot chart, and as we have seen in the organic rich rocks, the density and neutron both density porosity and neutron porosity both reach significantly high because of the presence of organic, and the NMR is not affected. So NMR gives you the true porosity. So if you take the difference between them, and that gives you a good quantification of the organics. So that's a very easy and quick way to understand, have a fair idea of the presence of the organics. Even in the field, when you're logging, actually, you can come up with just an overlay or cross plot, and you can, to some extent, you can quantify that. It doesn't, I'm not saying that you don't have to use the other methods, but that is a quick way and a very reliable method to have a good understanding of organics in the rocks. All these methods from the log are indirect measurement. So, but when you take a core and do analysis, for example, in the core you analyze with a either rock eval paralysis or a LACO-TOC methods, you have to compare all these log-derived volumes with the core, and you have to calibrate them. So have that in your mind, because log-derived methods are all indirect, and you have to do some correlation or calibration with a core data. Once you've done that for an area or particular basin, then you don't have to probably keep doing it if you are within the same area or targeting the same reservoir. But if you're moving out, then things can change. I'm just continuing with that. I'm just showing you here on the same slide, same diagram figure we saw before, the same three wells in the Eagle Ford. Now we're going to look at the third track. So third track, these two curves are derived from the blue curve and the black curve. Are derived from the kerogen volume coming from the difference between the the NMR porosity and the crossplot porosity, and that is the blue curve, and the black curve is the NMR difference between the NMR and the density porosity. Like I said, the lithologically, it is all these organic shales are quite significantly different from one another. For example, the Eagle Ford, you see you see clay volume, but there's not much. But when you look at the Marcellus, it has quite a significant amount of clay volume. So clay means what? Clay means it has a lot of water in it. So when you think of neutron, the neutron response will read quite high, and as a result, your cross plot will be skewed more towards a higher porosity as well, right? So you don't rely on neutron for a cross plot in neutron in a very high clay or high shelly area. In that scenario, actually a density porosity seems to work better, even though it's still having the kerogen volume within it, but to have the difference, to estimate the kerogen volume, taking the difference between the NMR porosity and the density porosity, in some of the rocks, especially the clay-rich rocks, it's better to use a density porosity. So that's what I'm talking about. So here again, these red dots are the coming from core, and you see it's a fairly good correlation here, and the same thing in this well, and same thing here as well. And as I said, this is a very strong correlation and very good, quick way of quantifying kerogen in the field itself with the presence of when you run an NMR log. Then we talk about the mineral volumes. Mineral volumes, again, most of the major oil field service, the violence companies have their geochemical tool. So these geochemical tools, some of them have come up with a measurement of carbon as well. This is relatively new. Before, carbon measurement was not possible. Now some of us have come up with a carbon measurement also. And you have the elemental data. I mean, all those students who are in doing geology, they know about the norm calculation. So it's pretty much the same. You have all these elemental or the oxides, you convert them to oxides, and then oxides you combine to form different minerals, right? So same way you can do it here as well. You have the elemental data, at least the measure 10 or 11, 9 or 10 oxides you can get from this geochemical tool, and along with some stress elements. And then you can combine them to form the mineralogy. But it doesn't tell you what mineral it is, right? It gives you all the elemental data. So what mineral you form, The best way is that you have some prior idea from either from mud logging, cutting analysis, or from XRD of the core. And when you do an XRD, you can quantify or identify, measure all the clay minerals and as well as the carbonates and the plastics, the sand, etc. So in this right hand side, I'm just showing you all these dots, are from the core data, and this is how you calibrate your geochemical data to the core data. So you don't have to do it for each or subsequent wells. Maybe in one of the well you calibrate that and you have that model. Like, again, I'm saying like it's on a particular area for a particular basin only, targeting the same reservoir. Then you can actually use that model for subsequent wells to come up with a good mineral volumes. From a good mineral volume, you get a good grain density, and that also helps you in determining a good porosity measurement. So that's why, having a good mineral volume is very important or very critical. Now moving on to water saturations. So as I said, water saturations depends on mostly the resistivity log, but in the presence of organics, and that resistivity is reading very high. So the water saturations that you are deriving using resistivity models such as the Archies or Simandou or the dwell water model, you can get a very erroneous water saturation measurement. One thing you have to remember that these rocks are extremely low in permeability, right? So when you are drilling, actually, there is very little invasion or really no invasion of the mud filtrate into the near wellbore rocks. So whatever your near wellbore water saturations, that probably is reflecting your uninvaded zone water saturations as well, particularly in the organic rich shales, because they are nearly impermeable. So when we do water saturations, we take shelter of another tool that is called the dielectric tool. So the dielectric, all these major service companies have their tools and they run it at different frequency. It's a frequency dependent tool, what frequency you run it with that. What it measures is the dielectric constant of all the minerals and the fluids within its depth of investigation. It has a very shallow depth of investigation, and that's why I was talking about that invasion thing, because if you are measuring in a very shallow depth of investigation, that ideally in a conventional reservoir, you'd expect that will be all flushed because of the draining fluid mud filtrate, right? But in organic rich rocks, because of the low permeability, that doesn't happen, and so you are representing actually a uninvaded zone water saturations. So I'm just showing a table here on the right hand side. I'm just highlighting this the dielectric constant of water. So if you compare that dielectric constant of water with the rest of the minerals here, you can see it's a significantly different. But remember that this is done at a 1 gigahertz frequency. So you can run the tool at multiple different frequencies. Then you have a real dielectric constant and an imaginary dielectric constant. At 1 gigahertz, your imaginary dielectric constants values are quite significantly low, and the real imaginary is there. Our real dielectric constant number comes up really good. So at this, the water stands out as compared to the others. So as you can see, we can very easily detect water. So this tool is used to estimate the water volume from in the rocks. So now you have solved the second puzzle as well, right? Because you have the NMR provide you with a total porosity, and dielectrics is providing you with the water fill porosity. So in the pores, we expect generally two fluids, either hydrocarbon or water. So if you know the total porosity and you know the water fill porosity, then it's become very easy to understand how much of a hydrocarbon there, right? So that's why, in these unconventionals, we have to we have to make use of these high-end tools, the NMR, dielectric, or geochemical tool, etc., to come up with a good model. So now, actually, this is also presented in an SP paper, how we integrate all these informations with the standard conventional tools as well as with the advanced tools. So this is how I mean, kind of a workflow that has been shown here, how you combine them. So on the left-hand side, the conventional measurement, and on the right-hand side, you use the NMR dielectric, those advanced tools. So here on the left-hand side, you determine the kerosene from the delta log R or regression model, and then on the other hand, you in the same well, you measure the or quantify the kerosene volume from density neutron or NMR, difference between the density neutron cross plot, I mean, and the NMR or a density or NMR, depending on different rock types. And then you can compare, right? And then compare and constrain one another to come up with a good model. And then you get the total porosity from NMR, of course. And then mineralogy from geochemical log, we know now at this point that when we use the geochemical log and we come up with a good mineralogy, we have a good estimate of the mineral volumes. We know exactly within a very narrow envelope of uncertainty how much or what minerals are there and what is their grain densities. So when you know the mineral volumes, that you have to feed into the dielectric model. The dielectric, what happens is that when it measures the dielectric constants, it looks at the dielectric constants from everything that is within its depth of investigation. What I mean by that is that it looks into the solid mineral part. The dielectric, suppose is the mineral, the rocks within its depth of investigation is consisting of quartz, clay, carbonates. Then it will have dielectric constant from those weighted to their volume, and the dielectric constant numbers coming from the fluids, whether if it is water and hydrocarbon, all these will be coming combined. So you will get only one number of dielectric constant that will volume weighted to the volume will have a total sum of all the minerals and the fluids within its depth of investigation, right? So then to filter out the rest and to come up with a water field porosity, you need to have a good mineralogical volume. So that's why, and when you have a geochemical tool that actually feeds that now that well ascertained mineral volumes into that dielectric model. So then it takes out assign all the mineral related dielectric constant to them, and the rest is assigned to the water. So that's how you come up with the water volume from there. So that's why, that is what I was referring to earlier, saying that we're going to discuss why we need the mineral volume so important, why we need to have the mineral volume so important. Actually, this is another method for which, we use that in a determination of the water saturation, water volume from the dielectric. Then, of course, when you have a good mineral volume, then you have a good grain density. And in this model, what we do is that when we have the NMR, we get the total porosity from that. We constrain this with the total porosity. So we said to the model, we use an idea of probabilistic error minimization solver, right? So you solve for mineral and the fluids along with porosity together. So we constrain the model to read the NMR porosity as it is, or maybe within a very small envelope of, giving a 1 PU up or down, and then we constrain the model with that. So, and that way, we are sure that our mineral volumes are right. Oh, sorry, the porosity is right. And then we get the mineral volumes coming from here are right. And then the kerosene volume is constrained as well. So that's a kind of a very robust model, and it seems to work perfectly well in nearly all the organic rich shale plays that I have come across. Even looking at the Vaca Muerta, this method still works perfectly. So that's how we integrate all of them to come up with a good petrophysical characterization model for organic rich shales. Here, just a little bit more elaboration on the how it compares from the when we combine the dielectric and the NMR. So here, what I'm showing here on the first track, this is your porosity coming from the NMR, and then this is your dielectric porosity, and we have the mineral volumes already known. So our dielectric water porosity is good. So here, now the separation between them, the total porosity from NMR and the dielectric constant, that is actually the hydrocarbon volume, right? So that now we are plotting it from 0 to 100% up to 20%, and this is, we see that the volume of hydrocarbon in these rocks. So this is NMR constraint, and dielectric has been taken into account as well. And it matches perfectly with the core data. But on the other hand, if we derive a porosity without the NMR constraint, just from the mineral volumes, and we take out the dielectric water from it, and this is what we get, and here is the volume, and this volume are not matching as it is here. This is the same well, by the way. I'm just showing you like two different scenarios. One, porosity is constrained to NMR, and dielectric is determining the water volume. Here also dielectric is determining the water volume, but the porosity is not constrained to NMR. So you see a significant difference. So the hydrocarbon volume we get derived from this is actually not matching with the core saturation measurement. And then on the right, this is the last track. We're showing the kerogen volume, how well it compares when we constrain it. So basically, what we have already said. So the kerogen volume we can derive from the difference between the cross-plot versus NMR, or density porosity minus the NMR. And hydrocarbon volume we can determine from the NMR porosity minus the dielectric porosity. So dielectric is all water, NMR is total, so the difference between them give you the hydrocarbon porosity. So here, I'm just giving you an example. This was done in the, I think, the Utica Point Pleasant. We published this paper and presented in SP as well. Here, this is our zone of interest, and this model here is not constrained to the NMR porosity, and it was, we didn't had NMR, I think, on this well. So the kerogen volume and the porosities were not constrained, and we solved for the mineral volumes. We didn't see much of a kerogen here, and when we compare our, this is the black curve here is the total porosity that is coming out of this model, and the effective porosity is shown here with the blue curve, taking out the clay volume, clay water-bound, clay-bound water volume out of it. And when we compare with the core data here, so this is my core, all these red dots are coming from core. You see, it's not matching at all. I mean, it's almost, we are estimating double, more than double actually, than what the core is measuring. So it gives you a completely incorrect porosity measurement here, right? And when you compare the grain density estimated coming from here, we see a significant difference as well. These grain densities, these dots are coming from the core, and this is estimated from the log. We see a difference of about 0.07 gram per cc in an average. So that 0.07 gram per cc average difference is throwing off your entire porosity quite significantly. So that is the reason why we have to constrain this model to get a correct mineral and fluid volumes. And again, here I'm showing the kerogen volume. This black curve is coming from this model here, and these dots are coming from the core, and we see a significant difference in them. So that's this is just to show you like how difficult just if going with a conventional approach, this can provide you such a erroneous result, which can throw off all your estimates, and it could be entirely wrong. So the thing comes like, these advanced tools like NMR, dielectric, and etc. are pretty expensive to run, and it takes a lot of time as well. And so you cannot run them in all. And a lot of areas we have some, particularly in the United States, you have legacy wells where some targets were either below into the conventional reservoir, but it has passed through some unconventional logs, and those logs are there, and those are cased hole now, and they are producing. So if you want to assess those unconventional sections above, then you have to rely on those old logs, right? So you don't have an option now to go and run a advanced logging tool there. So that is one of the reasons why we try to characterize from the conventional logs also. Also, I mean, in a new area, when you are using this advanced log in the subsequent wells, maybe you want to cut down on your logging um, program, then if you're taking out this NMR and all, then first you build the model there, and then you can propagate to the subsequent wells using just a standard triple combo or a quad combo kind of log. So for here now, if recommendation, but this is not necessarily be all, it's just a recommendation only, that we run this bare minimum, that your spectral gamma ray that will provide you with a potassium, thorium, and uranium measurement, and then a density neutron resistivity, of course, that's the standard triple combo, and a dipole sonic. Dipole sonic ideally would like to run with a navigation package so that we have a fast and shear slowness as well as the direction of fast and slow, so that you can ascertain the direction of your principal horizontal stress and minimum horizontal stress. This is very critical information for when you are stimulating the rocks to understand which direction you want to put your horizontal well and where in which direction your fracture is going to extend, right? And then, of course, sidewall core. If you're not done a whole core, then at least do the sidewall core. Most of the logging companies have sidewall rotary cores and good recoveries nowadays, and it's you get a good volume of rock from these cores to do a lot of all these different analysis. So core analysis, ideally at a bare minimum, I would recommend to have at least the XRD for total clay, quartz, and carbonates. And then, of course, the porosity, grain density, and permeability from the core. And then using a pyrolysis or Lacko-TOC method, come up with a TOC, or total organic carbon. You can determine, and from there you can derive a kerogen volume from it. And then, of course, the rock mechanical properties. For example, the Poisson's, Young's, minimum, maximum horizontal stress. You can also, I would also recommend doing a SEM analysis on the kerogen for a kerogen porosity, because that's very critical in most of these organic rich rocks to understand what kind of porosity you have, or how interconnected, or how much by volume kerogen porosity is contributing to the total porosity in the system. That's very important as well. So a conventional or a general processing steps would be first determine the kerogen volume, because that affects all your other log measurements. And now we are talking about only doing the model built from a conventional triple combo or quad combo rocks, right? We are without the advanced tools. So determine the kerogen volume, either density log R method, or sorry, the delta log R method, or smoker equations or density regression, etc., and calibrate to the core data. Then once that is done, then you can correct the density neutron response for the kerogen volume, and after that you can determine a clay volume from there. And once that is done, then you can bring that into determine. So you bring that in as an input, the clay volume and the kerogen volume, into your mineral model, whether it's a deterministic approach or a probabilistic approach. You can bring them into that model and solve for the rest of the minerals and porosities. Once you have a good estimate, when you have the clay volumes calibrated to core, you can be fairly confident of your mineralogy, and from there, then you can have a good grain density, and that also you can calibrate to the core. You can see how much of a grain density that has been measured in the core, and once that is done, then you get a fairly good porosity. So this way, without going into the advanced tools, also you can come up with a model, but you will be limited with a number of, for example, you will not be able to solve probably for all the different minerals. For example, like if you want to solve for feldspars and all, and on different kind of clays, whether like it's a montmorillonite or a elite or a chloride, probably you'll have to limit yourself to only a total clay. And for the carbonates, also maybe a total carbonates or a total quartz volume. The reason being that your number of input equations are limited, right? But that still works because you have a good estimate of the total clay volume and the rest of the minerals, and you come up with a fairly good grain density, and from which you can come up with a good porosity measurement. But all these, again, need to be calibrated to core data. Let's look at some of the laws, just in the rain. Oh, sorry, I forgot about the rock mechanical properties. Yeah, I mean, that you can determine once you have the sonic and density measurement and rest of the minerals volumes are coming from the log, you can definitely look into the rock mechanical properties as well. So rock mechanical properties, I'm not going to discuss now. I'm going to discuss towards the end when we discuss the tight gas sand as well, because rock mechanical properties determination methods are similar. So we're gonna discuss that at the last together, just to say, in order to save time. So this is an example in the Marcellus. So the first track here is the gamma ray track, or the correlation track. So here I'm plotting the gamma ray. So this is the total gamma ray. It's coming from the spectral gamma ray measurement, and the KT is the potassium thorium together. So here, this is my total gamma ray, and this is my potassium thorium. So ideally, the difference between them is your uranium, right? And here I'm plotting the gamma ray scale from 0 to 150, and you can see in this area that the gamma ray is off the scale. It's reading really high. So I expand the scale and going from 0 to 750, and now I can see the entire, all the peaks. So this is, so I can know now that this is a very hot gamma ray region. And I know that this is significant. You see the potassium thorium together is still showing normal, but uranium volume has gone up quite significantly. Here in particular, then here some other area, and this is another one, maybe here and here. So those are the hot gamma ray regions, right? And in this track, now I'm plotting the potassium thorium and uranium curve. This red curve is the uranium, just showing the same story. This high, so immediately this is a flag for me. I would think that, yeah, those are probably the organic rich or the source areas. And then I look at the resistivity measurement. So now you see, ideally, if you have a high clay, what you expect your resistivity to be. Your resistivity should go down because you are having higher clay means higher water, your resistivity should read low. But now in a high clay area, at least it is as shown by the gamma ray, but your resistivity is reading significantly high. Same thing here, same thing here, same thing here. So this is my most important flag, because high shelly area, clay area with a high resistivity is a very good indication of presence of organics. And now in this last track here, I'm showing the NMR neutron and density. The NMR is that dotted curve here, the dashed curve. And I'm just shading the difference between the density porosity and the NMR porosity. So these are the sections, where density porosity is reading higher than the NMR. And you see those are matching exactly where I'm seeing the high uranium content. So that's why, if you remember the comment I made in the very beginning about the Marcellus, that it is a high gamma ray and uranium correlates fairly well with the volume of kerogen. So this is how you can quantify the kerogen volume in this case. Then let's look at the next one. So this is again in the Point Pleasant, and this is just below the Marcellus. When I say just below, it's still about 1,000 to 2,000 feet, based on different areas, of course. And this is an older rock as compared to the Marcellus as well. And here, the difference are, the uranium is not the strong indicator here. So you see one thing here, when you look at the resistivity, here in this area, the resistivity is off the scale. And here the clay is, my gamma ray response is not that high. Actually, it dropped here, but my resistivity is way off the scale. And when I look at my density and the NMR plot, I see a significant difference here between my NMR and the density. Density is rating very high porosity as compared to NMR. So that's difference plus the high resistivity gives me a very good indicator, or I will raise the flag here that, yeah, this is a organic rich section. And so unlike the previous slide where we saw uranium to be a very strong indicator, here it doesn't seem to have uranium as a strong indicator, right? Here, in fact, density is, appears to be a more stronger indicator. Then we're going into the Eagle Ford. So Eagle Ford is here you have actually multiple indicators here. So here you have a high uranium, and then you have a fairly high resistivity as well. But below in this section you have carbonates and also that's why the resistivity is high. But this, let's consider only this section here. This is a high clay area. Ideally, this resistivity should have dropped to here, but it's reading high. So that's a flag, as I discussed earlier. So it has to have some organics or some component that is pushing your resistivity to be high. And when we look at the density porosity and neutron porosity, they go up quite significantly. So now with my NMR, there is a significant difference. So that's what, there's ample of evidence pointing to presence of organics here. So just from the triple combo, basic triple combo, or NMR with LMR, you can have a fairly good idea of that. But even if you do not have NMR, we have one example I was going to show you that we do not have NMR there. Even then you see a significant drop like this, where your resistivity is going up. If you have a uranium signature, that's also complementing it. But you can definitely understand that this is a area where organics are expected. Then this is an example in the Woodford. Here also I'm plotting the gamma ray from 0 to 800. We didn't have NMR here. We didn't have other advanced tools here. But gamma ray is fairly high, and look at the resistivity. It's reading significantly high as well, right? And when you look at the density neutron, density porosity and neutron porosity, they are increasing quite significantly as well. So the density, as a density measurement, has dropped, so showing an increase in density porosity and an increase in neutron porosity. So it pops up, right, very clearly. So, this is another organic restrictions that we can identify looking at just a conventional kind of log. So, and by now I think it gives you an idea of how, what are the challenges and how we can mitigate them. From either using advanced logging tools in combination with the standard triple combo or quad combo kind of log. And in the absence of those, also we have enough signatures that we can pick up from to understand, or understand the presence of kerosene or quantify them. So with that said, I'm going to go into the tight gas sand. Tight gas sand, I don't have that many slides because I can skip quite a few things there for the mineralogy and all. I'm not going to talk in detail. But here, the challenges are a little bit different. We don't have the organics now. So don't think about organics now. We're going to talk about the other challenges. OGIP, OGIP, original gas in place estimate. So if you think about these tight sands, they are depending on the depositional environment, whether the sea level rising or falling, you have quite a significant variation in grain size. So what grain size implies? Grain size variation means your pore size variations. So if your pore size is varying, then your deliverability of the reservoir, that is the permeability, varies quite significantly. And that is one thing. But here, these rocks are, or these sand beds are actually mostly, very frequently interbedded with clay or shale. So shale and clay, these shale and clay are not having organics, so they are having normal, inorganic shale, and they have a lot of water in it, so which pulls the resistivity down, resistivity measurement significantly down. And if you look at the resistivity vertical resolution, it generally is about 2 feet, or it can be resolved to 1 foot. But conventional tools are about 1 or 2 feet. Unless you have some image log, resistivity-based image log, those are much higher resolution. But otherwise, it's about 1 foot or 2 feet. And as a result, you may have multiple clay or shale interbedding this sand, so which pulls the resistivity down. And because of the vertical resolution now, the entire section, even though sand might have hydrocarbon and should have shown higher resistivity are actually masked by this lower resistivity from the clay. So what will happen? So if you just derive gas in place or saturation based on gas in place estimate, then you will be estimating very low gas in place in those areas, or so you may even bypass or discard that section, considering to be a non-reservoir section without having hydrocarbon in it. So that's one big issue, challenge in the tight gas sand. And as I mentioned, pore size variations. So pore size variations derives your permeability and also your fluid, or bound fluid versus free fluid, right? So if you have smaller pores, that means larger areas to cover by the first invading fluid, that is water mostly, has a larger water saturations, but those water will not produce because those are bound to the surface of the grains, and they are extremely small pores, so much larger surface area. So so that is very, that's why that bound versus free fluid is an important parameter here. So you may see a similar porosity in one section, between two sections, and one section is producing quite prolifically, the other section is not producing. That's because even if your porosities are same, your actually the pore size are different, and as a result, your bound versus free are different. Same thing also, like in some areas, you will see a very high water saturations, but you are producing no water. But you are, on the other hand, you're seeing some areas where you're seeing less water saturations, but you're producing plenty of water. So this is happening because even though you're having the same porosity, but your actually pore size are different. So that is a very critical information that we need to know in these tight gas sand reservoirs. And permeability. So permeability, generally people like to use a porosity to permeability transform equations. Generally people think that it's a more or less a linear relationship, but in these scenarios, it's not. Like I have mentioned, probably you have an idea by now, that it's not depend on how much of a pore volume you have, but it depends on what kind of pore size you have. So a pore size very based permeability is needed to come up with a good estimate of the permeability. And then, of course, the wireline, so rock mechanical properties. You can derive from the wireline log using the sonic and density mostly, and then, of course, those need to be calibrated to the core data. Core also, you can do some triaxial stress analysis and things like that, and you can calibrate that to the what you're deriving from the from the from the log. Sorry. So let's look into them a little bit more details, like what are the challenges. So the porosity, permeability, and bound. So we can propose running an NMR tool again. I mean, like you remember, we run the NMR there for a little bit of different applications. Here also we are running it again, and NMR, it's going to provide you with a total porosity, but NMR with the T1 and T2 activations. I'm not going into detail on the NMR technology here because that's beyond the scope of this presentation. But it can provide you with a grain size variation. So NMR T1 and T2 measurements are actually grain size variations and the fluid type variations based. So particularly from the T2, actually you can derive pore size variations with time. So generally the smaller pores, the NMR signal will come earlier in time, and then the larger pores will have the signals coming at a later time. So looking at the distribution of the signal, you can derive, or you can have a fair understanding what are my small pores, big pores, or how much of this rock is consisting of, whether it's a majority of the big pores or majority of the small pores, those kind of informations. And then scanning electron microscope has a fairly good idea, can provide you with a very good idea on grain size distribution as well. And you can actually compare that with the NMR derived pore size variations also. So that can help you deriving porosity, permeability, bound, and free fluid. So NMR comes help you in a big way here, determining all these three critical parameters. And then low resistivity pay. For the low resistivity pay, as I said, it could be very integrated with fine lamina of clay, and which lowers the resistivity. Uh, so we generally propose to run a what we call a triaxial induction tool for a laminated sand shell kind of analysis model. All these major service companies have this induction measurement. We have one slide. We'll look into that a little bit more. Um, and then and a variable cementation exponent. That's you're now talking about the saturation equation. For example, the Archie's equations. You remember that M, that is the cementation exponent, that can vary in these rocks. Ideally, we take only one number. Say, mostly we use the number 2 in our equation, and actually it's not always 2 in these tight gas sand, and it can vary quite significantly. And that can be determined. Actually, we can run the dielectric tool again here for that determination. But dielectric here, the water saturations will give us a invaded zone water saturation, because these pore size are a little bit bigger than the unconventional, the organic rich cells. So ideally, you would expect some kind of invasion within the near wellbore. So dielectric water fill or water volume will be actually reflecting the filtrate going into that near wellbore area. But with a near wellbore saturation, the SXO kind of measurement, we can derive a variable M. So that variable M, then we can fit that into our saturation-based model that to give us a good hydrocarbon saturation estimate. And then finally, the rock mechanical properties. Here we propose to use a VTI properties, but that again, it's more on the analysis side, not on the tool side. Tool you measure ideally a dipole sonic tool with a Stoneleigh, and then by calculating, we can actually come up with a VTI property. So VTI is a vertical transverse isotropy. That basically takes into account the layering effect. So layering effect, is quite significant. We'll look into that. So first, let's look at the NMR, and this is also a paper presented at the GCAGs in 2018 at Shreveport, Louisiana. I'm not going track by track, but this track is showing the NMR distribution. You remember, the time increases from left to right, and this is the another track for NMR. This is the T1 T1 distribution. So mostly we're going to look at this T2 distribution for now. And so these are, when you see these yellow humps here, these are representing very early time. So ideally you think that those are the extremely small pores, which could be from the clay-bound water, right? So that's the clay-bound water signal or extremely small pores. Now here I'm just showing you some pore size variations. So here, this is extremely small pore. So this is one grain here, another grain here, another grain here. So this is a pore, and it's filled with such a small pore that it's all our bound water. So the blue indicating bound water. As the pore size increases slightly, you can see that you started to have some free fluid coming in. So here now, you see some free fluid, and this is, but you still have some bound fluid that are not coming out or that's not flowing. And when you have a larger pore, you are seeing a considerable amount of free fluid, but there's still a significant amount of bound fluid there. Ideally, NMR uses a cutoff value to cut off to differentiate between the free and the bound fluid, but that model doesn't work very well in the sense that sometimes when you're going into the bigger pore here, it will show the whole thing will flow. But we know for sure that there is a bound fluid here, which is the wetting phase, and it's not going to flow. So when you use there's a slightly different model. It's called the spectral BBI model. When you use that application, actually you can take care of this rugosity within that pores and take into account of this how much of a bound versus free in a much better way. So that's why using a spectral BBI model from the NMR data, actually you can come up with a very good free bound versus free water estimates. That's what we're showing here in this track. So here, the first gray area shading here is indicating your clay-bound water. And then this kind of light brown is showing you the capillary bound water, which is this one here, the blue And then finally the free fluid. The free fluid can contain both, right? It can have hydrocarbon as well as water. So that's what it's showing, like a free fluid. So that's why, you know, the NMR is very clearly and tells you like which area you will be producing or which area you will have a higher free fluid as compared to another section. And then we derive a permeability. If you remember, I mean, I said that when you have bound water, a lot of small pores, your permeability goes low. And so NMR helps us. So when we are considering the permeability, we will considering probably this section here, but not the signals coming from here. This will be more like a bound water. But this will, where you put this cutoff, or, you know, that depend on your experience or the experience in a particular area or particular rock type. And then you can compare it, of course, with a core permeability measurement, and you can fine-tune that to optimize it. So that's how, you know, NMR has a big say or help in this kind of rocks. I'm just going to show you a little bit of an idea on the pore size and permeability. If you consider this is like a cubic packing here, right? So the top one is a cubic packing, the bottom one is a cubic packing, bigger grain size, smaller grain size. If you look at the porosity, this is phi indicating porosity, 47.6%, here also 47.6%. So that's the same porosity. The pore volume, total volume of the pore are same. But if you look at the permeability, the K indicating the permeability, you see there's a significant difference. So I think with this diagram, I think you got a fairly good idea on how permeability change with the grain size, not necessarily with the, or the pore size, not necessarily with the total pore. So you have the same pore volume, but your permeability is, varies quite significantly. Okay, now looking into the laminated sand shell volume. So let's consider this as a block of rock, and this is all the gray colors indicating the clay, and then you have the sand coming in between. So a conventional, you know, resistivity measurement, it generally measures like this, right? It's a lateral measurement. But when you use the triaxial tool, it has a vertical component coming to it. So we have now a RV, the resistivity of the vertical and resistivity of the horizontal, measured by the tool. So that's an input into the laminated sand shell model. And apart from the resistivity of the vertical, resistivity of the horizontal, we also can calculate a formation dip coming from this tool as well. And now when we have that vertical resolution, a vertical resistivity and a horizontal resistivity, we can come up with a resistivity of the sand. So now we are unmasking the effect of clay on the resistivity of these individual sand layers, so which will be reading much higher now. And when you estimate hydrocarbon volume from them, you'll have a much enhanced or better hydrocarbon estimate as compared to what you do with a conventional resistivity measurement. So this is, I'm just giving you a very brief idea. It by itself is a whole science, and a lot of processing, a lot of interpretation, a lot of inversions goes into that. The one other benefit is that when you get that R sand, it gives you in a much better vertical resolution as well. So this is a much better way to estimate, and you can, you know, all those bypass zones maybe earlier, you can, if you can, if you use this model, you can actually come up with a better hydrocarbon saturation model. So yeah, the same thing I'm saying here, the higher vertical resolution arsand is used to determine the true saturations of the rocks. The variable cementation exponent. So that is when we use a dielectric measurement, right? I mean, as we talked earlier. So we're going to look at, let's look at this last track here. So this is what we derive the variable cementation exponent, the M value here with this black curve. You see how it's active, it's varying. It's not a constant number. And this is a zone by zone, or, you know, continuous log of the saturation, cementation exponent. And I'm plotting from 1 to 3. And when we plot the, you know, generally we use the number 2. You can see that there is a significant difference in different areas, right? In this area in particular, there is quite a bit of a difference. It's reading much lower as compared to what we would have either either assumed as a 2. So that's going to make a difference in your saturation estimates. So that's why a variable cementation exponent, if we can, we should derive that in these rocks for our saturation estimation. I think we're almost nearing time. Oh, it's already over. Okay, well, I'll go very briefly on that. So again, let's consider the same lithology block, shale, clays, and the sands. And so clay and sand, you can imagine, like clay is very ductile, right? And the sand is very brittle. So when you apply force on that, the sand will brittle, as it is more brittle, it'll break, but the clays will absorb that force. So when you apply a hydraulic fracturing, or when you try to create a fracture here, if had it been entirely a sand block, your fracture might have grown from here to here. But now, since you have those clays, the ductile layers coming in between, this absorbs that force, and that impedes the growth of the fracture, and maybe you'll see a high growth now only up to this point. But in a conventional approach, you cannot estimate this this property. So you have to resolve that, or you have to use what we call a vertical transverse isotropy model. So basically, it's a processing or interpretation model. If you have a dipole sonic data with a Stoney measurement, you can actually resolve into all these stress tensors, and most of these are measured actually from the sonic. The C66 actually you can derive it from the Stoney measurement, and then you can actually account for all this layering effect. So now, instead of giving the stimulation engineer a reservoir rock mechanical property that would show a fracture high growth for the entire section, you will give them a more calibrated model, Poisson's and Young's modulus, or a closure pressure that will actually show actual, that he can derive an actual or better fracture high growth estimate. So this is a color scheme showing the same one well. This is done with a standard model, and this is done with that VTI or the 3D model. We are measuring here, we are showing here the closure pressure gradient. So that is an important property for the reservoir stimulation engineers or the frac and designers. It determines at what pressure the fracture will remain open. So here, if you see, ideally a lower closure pressure gradient is ideal for breaking the rock and keeping it open. So the red color is indicating lower, the blue is indicating higher pressure you need. So here you don't see any blue, but on the other hand, here you see like so many blues coming in. This is after using this model. This is without the model. So this is the actual scenario versus this one. Okay, so this is how then you combine all these informations and feed this data into the reservoir stimulation model to come up with a actual fracture design or reservoir stimulation design model. So that's the role of our or how we can calibrate the petrophysical models for this both the organic rich shales as well as the tight gauge sand. I hope it helps, and with that I conclude my presentation here. I think now it's open for your questions. Nikhil, I hope you're still there.
Hello, sir.
Hi.
Yes, sir. Thank you, sir, for the informative session. Now we'd like to go for the Q&A session. So I would like to, so I ask the participants to ask your questions if you have any, or you can raise your hand and we'll unmute you. Okay, sir. Sir, we have got the first question.
Okay.
From Amir. So for different lithologies, do we need to use different log data, and how we can correlate it with other?
Well, if I understand the question correctly, I mean, we are talking about here conventionals versus unconventionals, right? I mean, I'm mostly focusing on the unconventionals, how we characterize them. And so I was showing you how these characteristics, characterization process works using the wireline log data mostly and calibrating to core. So of course, in considering a conventional method where you are having, for example, like if you think of a carbonate versus a plastic sand reservoir, carbonates are more, you will have to run the similar tools, but you also, in addition to that, carbonates are generally prone to fractures. So you probably would like to run an imager there to understand the fractures, and because those may help you in hydrocarbon production, or they may bring in water as well. So understanding the fractures is one component. And carbonates, pore structures are different. A lot of time they have the moldy kind of pores. You may have a high porosity, but you may not have interconnectivity. So those kind of informations are very critical as well. So accordingly, you can design your logging suite of tools that you want to run, or what kind of other analysis, for example, like the core analysis, you want to supplement or complement with them. So first you have to think about, like, what are the challenges, what are the uncertainties that you are trying to determine, and accordingly you can design what kind of tools you want to run, and what kind of an answer which tool is going to provide, or how you integrate all of these informations to come up with one solution. So yes, it can vary from one reservoir to another. But in unconventionals, the whole scenario is a little bit different. And as you can see from this presentation, there's a lot of work around here as well. I hope that answers your question.
Okay, thank you, sir. So our next question, is it really that much uncertainties in the subsurface that after all the tools and processes, it is still different values from the real downhole values? And if such, what percentage is the accuracy of our tools? From Tom Edwards, sir.
That's right. That's a good question. Yes, each tool has its own limitations, right? And each tool, for example, like if I give you the example of neutron measuring the porosity. So it's an indirect way of measuring porosity. So neutron measures the hydrogen protons, and it quantifies how much of hydrogen proton is there, and accordingly it come up with a porosity number. So why hydrogen proton is important? Because whatever fluid we have down in the subsurface, in the pore spaces, it's either water or it is hydrocarbon. Both has hydrogen in it. So if we can quantify that number of hydrogen, then you can have a good estimate of porosity. But now, if you might think about hydrogen protons in oil or water versus hydrogen protons in gas, so it's much lesser denser, right? And one gas as compared to water or oil, or as compared to fluid. So number of hydrogens in gas for the same volume will be much less as compared to water or fluid or oil. So as a result, at that point, your neutron will not give you a proper estimate. And similarly, also, if you have a high clay, then you have a lot of water, but those are all clay-bound water. So that will show, that's why in the clay, you see a very high neutron response, right? So this is how, are the tools, and each tool has its own measurement principles based on which it measures different properties. Density measures the electron density of the rocks, the minerals, and then from that it converts to grain density or mineral density or lithology density, and then it converts, we convert that to porosity. So that's why we don't go with only one particular tool, but we combine them and come up with a solution, knowing the limitations and knowing the uncertainties. Each tool has its own limitations in different environment. For example, the NMR. NMR also looks at the hydrogen protons, but it's look at it in a little bit differently. It looks at the with a magnetic field, and but it looks at only the fluid part. So it's not looking at the solid part. That's why it's a lithology independent tool. It looks at the hydrogen in the gas or hydrogen in the water or oil, but not in the bound fluid, or say in the solid part, or the hydroxyl within the clay minerals. So that is why, it's a lithology independent measurement. So that's how, you have to combine and see how you can come up with a good and model. We compare most of the time our log response to calibrate to the core. But when you look at the core measurements or core analysis, it carries a lot of uncertainties as well. So a lot of time people tend to take the core measurement as a gospel and try to compare everything to that. But that's not necessarily always true. There's thousands of different ways by which core analysis is done. So there is uncertainties involved is there as well. So you have to take your best experience, best understanding, and and come up with a model. I hope that answers the question.
Okay, thank you, sir. Our next question from Martin. So what's the microscopic volume of shale, and does it have any relation to methane absorption capacity?
Right. Yes, it has. I mean, particularly in one area where we saw in the Cotton Valley, it's a very high pressure reservoir pressure. It's about 0.9, 0.889 or 0.9 pore pressure gradient. That's significantly high. And in those areas, actually, some analysis was showing that actually methane or dry gas actually is replacing the clay-bound water. So actually those clays were actually showing much lesser clay-bound water as compared to, suppose we consider elite. Elite ideally should have a clay-bound water of about 11% in normal situation. But in those situations, that clay-bound water in elite was going down to about 5% or 6%. And we saw some higher absorption of having or attachment of methane to those clay surfaces. So yes, it can vary, and the layering effect plus I don't have an exact number of what limited minimum clay thickness should be for absorbing higher amount of methane, but with pressure definitely it varies, and I think depending on the scenario or different situation, that absorption can vary as well.
Okay, sir. Thank you, sir. So next question: how to determine visually cavings from that coming from the shakers on the field, and what issues can it bring to our wellbore instabilities?
Oh, okay. That will be a good question for mud logging, I guess. But well, I had my career in mud logging also when I started. Yes, cavings or cavings falling up, coming. I mean, you can distinguish the cavings from the normal cuttings. I'm just trying to remember my earlier days, which is more than 15 years before. Those cavings are different, and depending on those caving size, actually, you can see whether it is, you're encountering some overpressure zones, or your mud are not sufficient enough. The mud pressure is holding back the reservoir pressure. That is one assumption. And also the other thing is that the swelling of the clay, right? A lot of these clays like the montmorillonite or smectite absorbs a lot of water, and then it swells. I believe if you're seeing larger volume of cavings, that's showing that you're having a lot of your well is not sufficiently engaged, and you're having some issues with wellbore stability. So ideally, yes, lesser cavings, more treated mud, more balanced mud should be able to take care of that.
Okay. Our next question, sir, could you explain the difference between DTC and DT, and why we need DTC?
Well, I think this is just the terminology that you're talking about. Well, the DTC is delta T compressional. So if you remember your acoustic waves, there is a compressional wave, and a shear wave, right? And so compressional is the DTC, and the shear wave is considered as generally DTS or DTRS in some areas. But in our wells, or when we run a sonic tool, a lot of time we come across some limitations. For example, if you have a clay very sticky, or not very compacted, then the shear slowness in those clays, uh, it's become extremely slow. So when it is slower than the mud slowness, then actually you cannot record those slowness. So now that has been overcome by using the flexural slowness method. So that's another, I mean, that by itself is one presentation. I'm not going into that now, but that measures that's an equivalent, or represents the flexural slowness represents the shear slowness, and it can do directionally as well, having orthogonal activators, and then you can measure the slowness in two different directions, perpendicular to each other direction. So compression is a sonic measurement, and so sonic gives you, the dipole sonic gives you a compressional measurement coming from the monopole tool, and then the shear measurement. So shear measurement, as I said, can be measured in two different directions, X and Y. That helps you in determining the fast and the slow direction that refers to your minimum and maximum horizontal stress. But to compute the rock mechanical properties, you need both compressional and shear. Then only we can derive the Poisson's ratio, and from there you can derive the closure pressures and all the other stresses. So DTC is compressional, DTS is shear, basically. So.
Thank you, sir. Sir, we have got a career-related question from Avinav. Sir, how a fresher from petroleum or geology background can build career in petrophysics, and what are the basic topics we must master before entering petrophysics, and which software are used by petrophysics? From Abhinav, sir.
That's a pretty broad question, right? I mean, I can just give you my example. I mean, I'm a geologist by education, did my PhD, and then I started my career as a mud logger, then become wellsite geologist, and then I switched to petrophysics about 13 years back. At that time we learned geophysics. I mean, we had exposure to seismic and electric logs and gravity log, etc. in our university. But apart from that, we didn't have much of, in real sense, the wireline logging environment, right? I saw that first when I was in the field, when the wireline log came to log the well. Out of curiosity, I started looking into the manuals and things like that, and then I started developing that because, and also when we were doing wellsite geology, then you actually come across the LWD or the MWD tools, and those provide you real-time measurement of logs as well. So that's how I developed by myself. So ideally, you can start having some understanding. There's a lot of literature available, and a lot of books are available as well. I think the first thing is that, you try to understand what is the logging environment, what are the different logging tools, what they measure, and you have one thing in mind. As a petrophysicist, you try to determine reservoir storage, that is your porosity, reservoir saturations, that how much of a hydrocarbon or water is filled there, and how much, and then reservoir deliverability, whether that reservoir can deliver, that is your permeability. So these are the main three components in reservoir characterization by a petrophysicist. So keeping those in mind in the background, and try to understand like how different tools are used for porosity determination, or how saturation is measured, or how permeability we can derive. Why we have so many different tools, and all of them are different, right? And NMR is nuclear magnetic resonance. That is something like the MRI that you do in hospital, or in lab. So the same technology we bring in here into the well. For the sonic is a computational and share that kind of thing, and then the neutron and NMR are hydrogen proton. You bombard with a neutron into the formation, and then you take response in the neutron tool. And NMR use a magnetic polarization method for hydrogen protons. Resistivity push resistivity in the form of lateral log or in the induction into the formation. So have an idea on these things and gradually start developing that. And if you're still a student, I would think that, yeah, why don't you try doing some internship in some of the company, or maybe do a project in that direction where you can get access to some log data and do some petrophysical interpretation. I know in US, there are some very few universities where you can do actually petrophysical interpretation, or petrophysical as a paper or as a subject in your curriculum. I'm not sure if it is done in India now. At least during my time when I was a student, I didn't know that we had one.
Thank you, sir. I think that's it for today's session. I do not see any questions.
Thank you very much.
Okay,
thank
you, sir.
And thank you for all the participants for your time today. I appreciate, and I hope it helps you. And if you have questions, feel free. You can send an email to me as well. I mean, I'll be very happy to respond. I might not be able to respond immediately, but I will try my best to respond to you.
So thank you everyone for your valuable time and cooperation to make the event successful. I, on behalf of the Petroleum Engineers Association, thanking Bhaskar Sharma sir for providing us time from his very busy schedule. Thanking him for his very informative and valuable presentation. Hope all of you enjoyed this knowledge sharing session. I am thankful to all you for your active participation, and I extend my big thanks to all my team members for their extensive support, and especially to the Bhaskar Sharma sir. Thank you so much, sir, for your valuable time.
Thank you very much for Nikhil for holding this and inviting me to present. I really enjoyed and looking forward to it for more such presentations. Thank you very much.
Welcome, sir. Have a good day, sir. Take care.
You too. Bye-bye.
Thank you, sir. Thank you so much.
Participant, you can leave and use the video link as soon as possible. We will try to post on our YouTube channel. Have a good day. Bye-bye.